In this video, we'll be going over the following problem. Four identical semicircles have their diameters on the sides of a square with side length 1. What is the combined area of the four semicircles? To begin, let's call the distance between the corner of the square and the corner of the semicircles x, and the radius of the semicircles r. Right off the bat, we can write an equation relating x and r, and that equation is x plus 2r equals 1. And this is because if we combine the diameter of a semicircle, which is 2r, and the line segment of length x, we get the side of our square, which is of length 1. We ultimately need to solve for r so we can calculate the combined areas of the semicircles. And since we have two variables, x and r, we're going to need two equations. If we connect the centers of two adjacent semicircles, note that we form a right triangle, which I've redrawn for the sake of clarity. Applying the Pythagorean Theorem on this right triangle will give us that second equation relating x and r that we're looking for. But before we do so, we need to determine what the three side lengths of our triangle are. For starters, we know the shorter leg of our triangle is equal to the radius of the circle. If we look back at the figure in the problem, notice that the longer leg is composed of the radius of the circle, as well as a segment from the corner of the semicircle to the corner of the square. And so overall, the length of the longer leg must be r plus x. The hypotenuse of our right triangle is of length 2r because it is composed of this radius and this radius. And if we were to apply the Pythagorean theorem, we would get the equation r squared plus r plus x squared equals 2r whole squared. The rest of the solution from this point on is just algebra. You have two equations and two variables, and so you just need to use a substitution method to solve for r, which you could then use to calculate the combined areas of the four semicircles. The algebra does get a little tedious, and you end up having to use the quadratic equation, so I'm going to be showing you guys a cooler and less algebra-heavy solution. This alternate solution relies on the concept of special triangles, specifically the 30-60-90 special triangle. For those of you who don't know, in a 30-60-90 triangle, which has angles of 30, 60, and 90 degrees, if the hypotenuse is of length a, then the side opposite the 30-degree angle will be of length a over 2, and the side opposite the 60-degree angle will be of length a root 3 over 2. If we return to the blue triangle on the left, note that the hypotenuse is of length 2r, and that one of the legs is half as long with a length of r. Because it's a right triangle, we know then that the angle opposite this leg must be 30 degrees, based on our 30-60-90 triangle. The remaining angle then must be 60 degrees, with the side opposite of it, which we previously said was r plus x, being of length 2r times root 3 over 2, or r root 3. Now if we return to the figure in the problem, we can see that the radius of the semicircle, which I've drawn a green line over, plus the longer leg of our right triangle, is equal to the side length of our square. In other words, r plus r root 3, which we just found to be the length of the longer leg of the triangle, equals 1, which the problem tells us is the side length of the square. Now if we factor out the r, we get r times 1 plus root 3 equals 1. And dividing by 1 plus root 3 on both sides gives us r is equal to 1 over 1 plus root 3. Now we have four identical semicircles, which is equivalent to two circles. And so the combined area must be 2 times pi r squared, with r being 1 over 1 plus root 3. If we expand the squared term out, this simplifies to 2 pi times 1 over 1 plus 3 plus 2 root 3, which is equal to 2 pi over 4 plus 2 root 3. If we divide the numerator and the denominator by 2, we get our final answer to be pi over 2 plus root 3. And for those of you who want to verify your answer but have it in a slightly different form, This is approximately equal to 0.8417.